All right, hi everybody. Here is chapter 10, and this is question 39. These are a couple of different species that ask for electron molecular geometry as well as hybridizations. I'm not going to do all of these. I'm going to do two of them again, same as I did for the Lewis structures. And if you have questions about the remaining ones, you're welcome to email me and ask me about them. Okay, so let's start with the first one here, phosphorus trifluoride. So these I always start these with Lewis structures, right? It's good to rough it out in a sense, know what's going where, and then calculate your hybridization and such like that from that. But there are multiple ways to do it. Okay, so we've got 4 species here that need 8 electrons apiece. We've got 32 for the total. I subtract from that 3 times 7 for the fluorine, so it's 21 plus 5 for the phosphorus gives 26, right, for a difference of 6, which we're dividing by 2, so we should have 3 bonds. Easy enough. Okay, so here come the 3 bonds. P, F, 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 right, piece of cake. There's our extra electron. Tack on the necessities. All right, so we get 8, 8, 8 plus 2 for 26, so that checks out there. Okay, so that'll be that then. So the question then is what sort of form does this take? We have 3 ligands, right? Ligands being the things that are not free pairs that attach to the central atom. So per Vesper theory, all of your shapes will come from this. So we got 3 ligands, 1 free pair, total of 4 things, which means that this is going to be sp3 hybridized. And it's going to produce a structure that looks like this. We're going to have 1 fluorine there. Yeah, I mean, my writing's bad enough, let alone my drawing, but yeah, that kind of gets the idea there. All right, and then there's going to be this free pair up top. That does not count for the molecular geometry, so the molecular is going to be equal to trigonoplanar. Oops. Trigonoplanar. No, not planar, pyramidal. Good grief. Yeah, the other P. Okay, that's the molecular one. The electronic one includes this lone pair up top, so that is going to be tetrahedral. So we got tetrahedral for the electronic and trigonopyramidal for the molecular, right, with the sp3 hybridization. Okay, so that's the first one down. Let's have a look at the next one, whatever the next one is. Try and pick an interesting one. Let's see. Okay. Hydrogen trichlorocarbon. Let's do that one. HCl3. Be a good mix. Okay, in this case we need, we don't even have to do this one because carbon's going to be the central atom, and we know how this is going to look. This is going to be something like this. Cl, 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 just like that. You're not gonna hybridize carbon past this, so you're gonna have an sp3 hybridization again. In this case, your molecular geometry is going to equal your electronic, right? Because you don't have a free pair around carbon at all. This is the 4 ligands, 0 free pairs. All right, so this is going to be tetrahedral. Sometimes they're super easy like that. Okay, so that is 1039. That's an example of application of Vespers. Vespers, the non-liturgical variety. Make sure for the Vespers, this is especially important in inorganic chemistry next year. This is the important bit of Vesper theory is what results from this number of ligands and this number of free pairs and this number and blah, 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 blah. So do make sure you write that in.